Hello students, in today's lecture we will study about bond parameter. This is given in NCERT syllabus rationalized for the academic year 2023-24 of class 11 chemistry. In the previous lecture, that is lecture number 1, we have studied that Cosel's first insight into the mechanism of formation of electropositive and electronegative ions related the process to the attainment of noble gas configurations by respective ions. Electrostatic attraction between ions is the cause for their stability. This gives the concept of electrovalency. We have also studied that the first description of covalent bonding was provided by Lewis in terms of sharing of electron pairs between atoms, and he related this process to the attainment of noble gas configurations by reactive atoms as a result of sharing of electrons. The Lewis dot symbols show the number of valence electrons of atoms of a given element, and the Lewis dot structures show pictorial representations of bonding in molecules. We have also studied that an ionic compound is pictured as three-dimensional aggregation of positive and negative ions in an ordered arrangement called the crystal lattice. In a crystalline solid, there is a charge between the positive and negative ions. The crystal lattice is stabilized by the enthalpy of lattice formation. We further studied that while a single covalent bond is formed by sharing of an electron pair between two atoms, multiple bonds result from sharing of two or three electron pairs. Please note, multiple bonds result from sharing of two or three electron pairs. Some bonded atoms have additional pairs of electrons not involved in the bonding process. These are called lone pairs of electrons. A Lewis dot structure shows the arrangement of bonded pairs and lone pairs around each atom in a molecule. We will continue our previous discussions by studying important parameters associated with chemical bonds like bond length, bond angle, bond enthalpy, bond order, and bond polarity, which have significant effect on properties of compounds. In the end, we will study worked examples and answer multiple choice questions. This is a very important topic. Please listen to my lecture very carefully and note down all the important points. I welcome you once again. Bond parameters, and in this the first parameter is bond length. Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. Please see the figure above. The bond length capital R in a covalent molecule AB is shown. Here A and B are molecules, two elements, and their molecules is AB. Here capital R is equal to RA plus RB. In the case of a covalent bond, the contribution from each atom is called covalent radius of that atom. Bond lengths are measured by spectroscopic, X-ray diffraction and electron diffraction techniques, about which you are going to study in your future classes. Each atom of the bonded pair contributes to the bond length as shown in the figure. The covalent radius is measured approximately as radius of an atom's core which is in contact with the core of the adjacent atom in bonded situation. The van der Waals radius represents the overall size of the atom which includes its valence shell in a non-bonded situation. This is shown in the figure on the screen on the right hand side. The covalent and van der Waals radii in a chlorine atom is shown here. The inner circles correspond to the size of chlorine atom. These inner circles correspond to the size of the chlorine atom, and the covalent radius RC is shown here. That is, the distance between two centers is 198 divided by 2 is RC is equal to 99. As against this, the van der Waals radius RVW is shown here. The distance between the two adjacent atoms is 360 and it is divided by 2 is 180 picometers. Hence, further the van der Waals radius is half the distance between two similar atoms in separate molecules in a solid. Some typical average bond lengths for single, double and triple bonds are shown in the table in the next slide. Bond lengths for some common molecules are also given in tables 3 and 4. The table number 1 on your screen shows the average bond lengths for single, double and triple bonds. In column number 1, bond type is given. It may be a single bond between O and H, C and H, or N and O, C and O, C and N, and C and C. All these are single bonds between the respective atoms. The covalent bond for these bonds are given in column number 2 in terms of picometers. So covalent bond length is PM. So for OH it is 96, for CH it is 107, and for NO bond it is 136, for single CO bond it is 143, for single CN bond 143, for C and C it is 154. For all these values are given here. You may please pause this video and note down. Further, the double bonds are shown between, there are double bonds between C and O whose covalent bond length is 1 to 1, and the double bond covalent bond length for N between N and O is 122, between C and C it is 133, and C and N it is 138 picometers respectively. Similarly, there is a triple bond between C and N atoms as shown in the table number 1, and its covalent bond length is 116 picometers. The next type is between C and C. It is a triple bond between C and C, and its covalent bond length is 120 picometers. Table number 2 shows the bond lengths in molecules. Here the molecules may be H2, that is single bond between H and H, and its bond length is 74 picometers. For F2, there is a single bond between F and F atom and the bond length is 144. For Cl2, that is single bond between Cl and Cl is 199 picometers. For Br, that is single bond between Br and Br, two atoms of Br, the bond length is 228. I2, it is 267. N2 has triple bond between two atoms N and N and its bond length is 109. For O2, that is O-O, single bond 121 molecule 121 picometers. Similarly, the case for HF, HCl, HBr and HEI, and the respective values are 92, 97, 141 and 160. So you please pause this video and note down, copy these two tables. The next parameter is bond angle. Bond angle is the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or a complex ions. So I will read it once again. Bond angle is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule oblique complex ions. Bond angle is expressed in degree, which can be experimentally determined by spectroscopic methods. It gives some idea regarding distribution of orbitals around the central atom in a molecule oblique complex ion, and hence it helps us in determining its shape. An example of H-O-H bond angle in water is represented and shown on the screen. The bond angle here between H, O and H is 104.5 degrees. This is the angle between the two bonds. Bond enthalpy. Bond enthalpy is defined as the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. It is also known as bond dissociation energy. The unit of bond enthalpy is kilojoules per mole. It is important that larger the bond dissociation enthalpy, stronger will be the bond in the molecule. In a polyatomic molecules like 4CH bonds in CH4 does not possess the same bond energy due to change in chemical environment. Therefore, we use the term mean on or average bond enthalpy. It is obtained by dividing total bond dissociation enthalpy by the number of bonds broken, as explained below in the case of a water molecule. Thus, the average bond enthalpy for a water molecule is given by equals 502 plus 427 divided by 2, that is equal to 464.5 kilojoules. In the inside box, some examples of bond enthalpy are shown. For example, H dash H bond enthalpy in hydrogen molecule is Hg plus Hg. H2 in gaseous states splits to Hg breaks into Hg plus Hg, and its enthalpy, bond enthalpy is 435.8 kilojoules per mole. The other examples are O2, that is O double bond O in gaseous state splits to O gaseous plus O gas, and its bond enthalpy is delta AH is equal to 498 kilojoules per mole. And in case of N2, that is N forming triple bond with another N atom in gaseous state breaks into Ng plus Ng, and its bond enthalpy is 946.0 kilojoules per mole. It is important that the larger the bond dissociation enthalpy, stronger will be the bond in a molecule. For a heteronuclear diatomic molecules like HCl, we have HCl in gaseous state splits to form H in gas plus chlorine, and its bond enthalpy is 431.0 kilojoules per mole. In case of polyatomic molecules, the measurement of bond strength is more complicated. In Lewis' description of covalent bond, the bond order is given by the number of bonds between two atoms in a molecule. Hence, bond order is the number of bonds between the two atoms in the molecule. Isoelectronic molecules and ions have identical bond orders. A general correlation useful for understanding the stabilities of molecules is that with the increase in bond order, the bond enthalpy increases, whereas the bond length decreases. Please see the examples given in respect of bond order. H2 with a single electron pair, the bond order is 1. In case of O2 with two shared electron pairs, the bond order is 2. For N2 with three shared electron pairs, the bond order is 3. For CO, three shared electron pairs between C and O, the bond order is 3. N2 bond order is 3 and its bond enthalpy is 946 kilojoules per mole. It is one of the highest for the diatomic molecule. For isometric molecules like F2 and O2 2- have bond orders 1. For N2, CO and NO plus, the bond order is 3. It is often observed that a single Lewis structure is inadequate for the representation of a molecule in conformity with its experimentally determined parameters. For example, the O3 molecule can be equally represented by the structures 1 and 2 as shown on the screen. So, the O3 structure can be either be represented as structure 1 or structure 2. In both the structures, we have O-O single bond and a O double bond. The normal O-O and O-O bond lengths are 148 picometers and 121 picometers. See, single bond is 148 picometers and double bond is 121 picometers. It can either be representation like this or like this. Experimentally, determined oxygen to oxygen bond lengths in O3 molecules are 128. So experimentally determined values are 128 picometer. Thus, the oxygen-oxygen bonds in O3 molecule are intermediate between a double and a single bond. Obviously, this cannot be represented either by either of the two Lewis structure as shown in 1 and above. The concept of resonance was introduced to deal with the type of difficulty experienced in depiction of accurate structure of molecules like ozone. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, positions of nuclei, bonding and non-bonding pairs of electrons are taken as canonical structures of the hybrid, which describes the molecule accurately. Thus, for O3, the two structures shown on the screen constitute the canonical structures or resonance structures and their hybrid. That is, the structure 3 here represents the structure of O3 more accurately. This is called resonance hybrid. Resonance is represented by a double-headed arrow. See, this double-headed arrow represents the resonance. In general, it may be stated that resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure. So repeat, resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure, and resonance averages the bold characteristics as a whole. Thus, the energy of O3 resonance hybrid is lower than that of either of the two canonical forms 1 and 2. Many misconceptions are associated with resonance, and the same need to be dispelled. Please remember that the canonical forms have no real existence. The molecule does not exist for a certain fraction of time in one canonical form and for the other fractions of time in other canonical forms. There is no such equilibrium between the canonical forms as we have between tautomeric forms like keto and enol in tautomerism. The molecule as such has a single structure which is the resonance hybrid of canonical forms and which cannot as such be depicted by single Lewis structure. Work examples. Explain the structure of CO3 2 minus ion in terms of resonance. The single Lewis structure based on the presence of two single bonds and one double bond between carbon and oxygen is inadequate to represent the molecule accurately as it represents unequal bonds. According to the experimental findings, all carbon to oxygen bonds in CO3 2 minus are equivalent. Therefore, carbonate ion is best described as a resonance hybrid of canonical forms 1, 9, 2 and 3 as shown below. Here you can see the carbonate ion is best described as resonance hybrid of canonical forms 1 and 2 and 3 as shown below. Next question. Explain the structure of CO2 molecule. Answer. The experimentally determined carbon-oxygen bond length CO2 is 115. The length of a normal carbon to oxygen double bond C double bond O and carbon to oxygen triple bond C triple dash O are 121 picometers and 110 picometers respectively. The carbon-oxygen bond lengths in CO2 115 picometers lie between the values of C double dash O and C triple dash O. Obviously, a single Lewis structure cannot depict this position, and it becomes necessary to write more than one Lewis structure and to consider that structure of CO2 is best described as hybrid of the canonical or resonance forms 1, 2 and 3. These are depicted on the screen. This is structure 1, this is structure 2 and this is structure 3. The existence of a 100% ionic or covalent bond represents an ideal situation. In reality, no bond or a compound is either completely covalent or ionic. Even in case of covalent bond between two hydrogen atoms, there is some ionic character. A covalent bond is formed by sharing of a pair of electrons by two atoms, each one of which contributes one electron. If two atoms have the same electronegativity, then the sharing of two bonded atoms is equal. This situation is encountered when both the atoms are the same element, are of the same element, that is, as in the case of H2, Cl2, O2 and N2, etc. Such a bond is pure covalent bond and it is a non-polar in nature. On the other hand, if the electronegativities of two bonded atoms are different, as in the case of HCl, then the shared pair of electron lies more towards the more electronegative atom, that is chlorine. As a result, a small negative charge delta minus develops on Cl atom and a small positive charge delta plus develops on H atom as shown in the figure. The figure A shows the non-polar or a pure covalent bond and the figure B shows a polar covalent bond. So here you can see delta plus on H and delta minus on Cl. The covalent bond in HCl is a polar covalent bond and it is not a pure covalent bond as it has some ionic character. For formation of ionic bond between two atoms, the electronegativity difference between them should be greater than or equal to 1.9. The dipole moment of CO molecule is greater than expected. This is because the presence of a coordinate bond, dative bond. Dipole moment. Charge separation in a covalent bond results in the formation of an electrical dipole, two equal but opposite charges with a small distance between them. Each electric dipole is characterized by its dipole moment. Dipole moment is given by the relation is represented by a symbol mu. Dipole moment is equal to magnitude of the charge q into the distance of separation r. It is commonly measured in the unit dB, named after the scientist Peter dB, the Dutch chemist who received Nobel Prize in the year 1936 for his work on X-ray diffraction and dipole moments. The magnitude of dipole moment is given in dB unit in order to honor him. So it is commonly measured in the unit of dB. Symbol is capital D. The SI unit of dipole moment is Coulomb meter. Cm. Capital C is for Coulomb, small m is for meter. The two units are related as 1 dB is equal to 3.336 into 10 to the power of minus 3 Coulomb meter. The dipole moment depends on difference in electronegativities of two bonded atoms as shown in the data given below. Here please see the table displayed at the bottom of the screen. The bonds are here some 4 different bonds are shown H-F, H-Cl, H-Br and H-I. The electronegativity of this halogen atom is for H-F it is 4 and dipole moment in dB is 1.9. Dipole moment is a vector quantity since it has direction and magnitude both. By convention, the symbol shown on the screen is used to represent the dipole moment. Here, the tail on the positive center and the head pointing towards the negative center. So, this is the symbol of a dipole moment, and a positive symbol is marked on its tail and head is pointing towards the negative center. The dipole moment of HCl is thus represented as H-Cl, so positive on D and negative pointing towards Cl. Like forces, dipole moment vectors can be added and subtracted. By doing so, the overall dipole moment of a molecule can be calculated. Table 5 shows the dipole moments of selected molecules. Here, the first column indicates the type of molecule. The type of molecules may be AB type, AB2 type, AB3 type and AB4 type molecules. Some examples of AB molecules are HF, HCl, HBr, HI and H2. The dipole moment in dB for HF is 1.78, for HCl is 1.07, HBr is 0.79 and so on. The geometry of the molecule is shown as linear for HF. For HCl, it is linear. For all the AB type of molecules indicated in the table, the geometry is linear. For AB2 type molecules like H2O, the dipole in dB is 1.85 and its Lewis structure geometry is bent. And for H2S, the dipole moment is 0.95, its geometry is also bent. For CO2, the dipole moment is 0 and its Lewis structure geometry is linear. Similarly, for molecule AB3, example is NH3, its dipole moment is 1.47 and geometry is trigonal pyramidal. Similarly, for NF3 and BF3, the corresponding values of dipole moment in dB is shown as 0.23 and 0, and its shapes are geometry is trigonal pyramidal and trigonal planar. For molecule type AB4 like CH4, the dipole moment is 0 and its geometry is tetrahedral. Now we will take up some examples. Example number 1. For carbon dioxide, CO2 molecule is a linear triatomic molecule. There is a double bond between C and O is polar with the oxygen atom having a negative end of the bond dipole as shown in the diagram. The dipole moment of both the double bonds between C and O have the same magnitude but are in opposite direction as seen in the insert box on the right hand side of your screen. Hence, these opposite directions, dipole moment in opposite direction cancel each other. The net dipole moment of CO2 is 0. This 0 and it is depicted in AB type molecule here. The next example is for water. For water, H2O is a nonlinear or bent type diatomic molecule. Each bond between H and O is a polar covalent bond and has a dipole moment. Although dipole moment of both the bonds are equal in magnitude, but due to nonlinear shape, they do not cancel with each other. The net dipole moment of H2O molecule is 1.85 dB as shown in the table here, table number 5. H2O it is 1.885 or its value is 6.17 into 10 to the power of minus 3 coulombs per meter. Coulomb meter, not coulomb per meter. In respect of boron trifluoride, that is BF3, the net dipole moment for BF3 is 0 due to its symmetrical planar structure as shown in the Lewis dot structure diagram on the screen. Although the bonds between B and F are polar. Please note down these diagrams. Next example is for ammonia, NH3. NH3 has a pyramidal structure which makes the arrangement of three NH bonds. There are three NH bonds here. You see, there are three NH bonds. Nitrogen is negative center and hydrogen is positive center, as shown in the dipole symbols, corresponding dipole symbols. In addition to three NH bonds, nitrogen atom has a lone pair. This is a upper one is a lone pair of electrons, which also has an orbital dipole moment in which the electron pair is negative at the center. So this is the negative end and the upper one is positive. So the bond and orbital dipoles are shown here for structure 1, structure 2 and structure 3. The net dipole moment of NH3 is 1.47 trigonal pyramidal as shown in the dipole moment table above. Next and final example is that of carbon tetrachloride. This is shown on your screen in the bottommost part. For carbon tetrachloride, it has zero dipole moment due to its symmetrical tetrahedral shape. Please pause this video and note down all the Lewis dot structure diagrams and dipole moment diagrams. Fajan's rules. According to Fajan's rules, the magnitude of covalent character in an ionic bond depends upon the extent of polarization caused by cations. So, the magnitude of covalent character in an ionic compound is a function of extent of polarization caused by cations. In general, smaller the size of cations, larger is the polarizing power. Among two cations of similar size, the polarizing power of cation with noble gas configuration NS2 NP6 ND10 is larger than cations with noble gas configuration NS2 NP6. For example, polarizing power of silver plus is more than K plus. Larger the anion, more will be its polarizability. Let us quickly solve some MCQs. Which of the following is electron deficient? Four options are given. SiH3 whole 2, BH3 2 and PH3 CH3 2. So you have to select the correct option which is electron deficient. The correct option is B because it contains two 3' center -2 electron bonds that are present above and below the plane of molecules. Compounds which do not have sufficient number of electrons to form normal covalent bonds are called electron deficient molecules. Please note, compounds which do not have sufficient number of electrons to form normal covalent bonds are called electron deficient molecule. So BH32 is electron deficient compound. Next question. The correct sequence of increasing the covalent character is represented by. So four examples are given. You have to examine each one of them and mark it. So four options are given, and in this the correct answer is C, NaCl, because as difference of electronegativity increases, percentage ionic character increases and covalent character decreases. That is, as electronegativity difference decreases, the covalent character increases. Further, greater the charge on cations, more will be its covalent characters. Be has the maximum of +2 charge. Hence, option C is the correct answer. Which of the following is electron deficient molecule? So, four options are given. C2H6, B2H6, SiH4 and PH3. That is option A, B, C and D respectively. You have to choose the correct answer. Mark your answer and I will give the explanation. The explanation is the compound of its central atom is octetless, known as electron deficient compound. Hence, B2H6 is electron deficient compound. Please mark it. Option B is the correct answer. Next question. Cations and anions combine in a crystal to form the following type of compound. So you have to identify which compound. That is crystal to form ionic or metallic, covalent or double dipole. And you have to remember that cations and anions combine to form ionic bond in crystal. The electrostatic force that binds the oppositely charged ions, which are formed by transfer of electrons from one atom to another, is called ionic bond. So the correct answer is A. Please mark it. Next question. Among the following electron deficient compound BCl3, CCl4, PCl5 and PCl3, which one is the electron deficient compound? You have to identify. So boron in BCl3 has 6 electrons in outermost shell. Hence, BCl3 is an electron pair deficient compound. Hence, option A is the correct answer. Please mark it. Which of the following compound has 3' center bond? Diborane, carbon dioxide, boron trifluoride and ammonia. So you have to mark the correct answer. The idea of three-centered electron pair bond B-H-B bridges is necessary because diborane does not have the sufficient electrons to form normal covalent bond. It has only 12 electrons instead of 14 that are required to give simple ethane ethane-like structure. So the correct answer is A. Please mark it. Linus Pauling received Nobel Prize for his work on atomic structure, photosynthesis, chemical bond or thermodynamics. So you have to remember and mark the correct answer as chemical bonds. Next question. The weakest among the following types of bonds is, so you have to identify the weakest bond. Ionic, covalent, metallic and H bond. Options are A, B, C and D respectively. So H bond is the weakest of all. So you please mark it. Which of the following pairs will form the most stable ionic bond? Na and Cl, Mg and F, Li and F, Na and F. So the stability of ionic bond depends on the lattice energy, which is expected to be more between Mg and F due to +2 charge on Mg atom. So option B is the correct answer. Next question. Strongest bond between CSF, NaCl, both A and B and none of the above. Options are, so which is the strongest bond? You have to identify between CSF and NaCl. According to Fajan's rule, ionic character increases with increase in the size of cation and decreases in size of anion. Thus, CSF has higher ionic character than NaCl, and hence bond strength of CSF is stronger than NaCl. Please mark it. Among the following, which compound will show highest lattice energy? So options are A, Kf, option B, NaF, option C, CSF, and option D, RBF. For compounds containing ions of same charge, lattice energy increases as the size of ions decreases. Thus, NaF has highest lattice energy. The size of cation is in order of Na plus K plus Rb, Na plus less than K less than Rb plus and less than Cs plus. So the correct option is NaF. That is option B. Please mark it. Next question. Amongst LiCl, BeCl2, BCl4, BCl3 and CCl4, the covalent bond character follows the order. Option A, four options are given. LiCl less than BeCl2, greater than BCl3, greater than CCl4. Option B is BeCl2 less than BCl3, less than CCl4, less than LiCl. Option C is LiCl is less than BeCl2, less than BeCl3 and less than CCl4. And finally the option is LiCl greater than BeCl2, greater than BCl3 and greater than CCl4. You have to analyze and mark the answer. Pause the video and mark your answer. I will give the correct answer. As we move in the period from lithium, beryllium, boron and carbon, the electronegativity increases and electronegativity difference between the element and chlorine decreases, and accordingly the covalent character increases. Thus LiCl is less than BeCl2, which is less than BCl3 and which is further less than CCl4. This option is given as C. Please mark it. C is the correct option. With this, we come to the end of lecture 2. In the next session, we will discuss about valence shell electron pair repulsion, that is VSEPR theory and valence bond theory. Till then, you study this lecture, listen to this lecture too, and note down all the important points. Goodbye.